the most general cost function would be for the kind of 3D bar kind of setting would be x minus x background transpose b inverse x minus x b plus the distance between the observation and this, which I will write it as y minus hx transpose r inverse y minus hx, right? And have you worked out what this is? The minimum of this. What's the minimum of this cost function? Has anybody done it? Do you have it with you?
But I'm not sure when it's correct.
Just write it out and then we'll see. This not being there, this not being there, xb equal to 0 effectively, right? Yes, okay, go ahead.
I'm not sure when
I don't know either, unless I see it. Okay. Sumant, samgos.m or samgos_v1.m? Huh? Okay. I forgot which one it is that you should copy. Yeah, so I'm there. Is it this?
No, it's in rounds actually.
Yeah, I have copied it.
You're in Tornado?
I copied it from Tornado.
Okay.
Yeah. This is exactly the test MATLAB, the whole test MATLAB directory.
Yeah, this is the one.
This is the one, right? Okay, fine. So, and the test script is test one step. That's the one. Underscore 2 is something else.
No, that's it.
Yeah, I mean, I think that's right. Yeah. So, I think I should be able to check. Yeah, no, this is right. Yeah. So I know this term is right for sure.
This term is
right. And I know this one is right. So I think okay. So, but okay. So there is a trick which I won't describe right now, which then gives you that this same equation can be written in the following form. this is equivalent to writing x as xb plus something else. The something else happens to be that with k is equal to r plus b h transpose, H transpose, okay. And there is something else here which the way to fill up, the way to, okay, and this is the formula which is known as the Kalman gain formula, or this is the Kalman gain, and this is the update formula based on given a background and given observations. You want to combine both of them together with different weightage factors, right? And the way to construct this, I never remember it, the way to construct it is to remove the dimensions. So let me write down the dimensions here. So this is n cross 1, this is of course n cross n, y is n cross 1, so h needs to be n cross n, which basically means that this whole matrix is m cross m. So I better have a matrix here which is something cross m, where the only matrix that is something, that's a natural choice, which is H transpose, and then this is going to disappear in a minute, so I better write very quickly. There. Okay, so I think somebody doesn't want, involves the identities that Varun was talking about. These three people shared, I never remember this name. The Woody, something Sherman, Morrison identity of matrix inverses, right? Okay, so we will take this as, I will erase the derivation. So what's the idea behind? So this is one step, right? You are given certain observations at certain time, and you have some background at a given time, at the same time, and you are simply updating. What's the idea behind Kalman filter? Varun will do this in much more detail later, but is the following: you have time, so you have time, and suppose at some given time you have a xb associated to which you have a error covariance matrix B, and your observation which is say Y associated with error covariance R. So that's n cross 1, n cross m, n cross 1, n cross n matrices, and you want to update, that is, you want to find a better estimate which is halfway in between the two, halfway being, which is a so to say linear interpolation. You can see that from here, it's basically a linear interpolation between xb and y in some way. They are in different spaces, so it's not really, it doesn't make sense to call it a linear interpolation, but weighted sum of the two, right? And that's your, so let me call this xu. So this is xu, and you can also then show that the Hessian of this, so of j at xu, well actually this is quadratic, so the Hessian of a is independent of the point of j. Okay. It's simply I minus kh times b, right? So I think, I'm pretty sure Varun is going to do this in much more detail, but if not, then we'll do it in one of the question answer sessions or something, right? So then you get a the Hessian of j is your updated error covariance. So let me call this as say BU. Okay. And to be consistent, let me call this BB, and eventually I will change all these to P's because they are covariance matrices, and which are usually denoted by letter P, right? So, and once you are given this, if you want to go to the next observation time, this is time t2, you would, and you have a observation here, so let me call this as y1 and r1, and I have an observation y2, r2 at this time. I want to take this state, this updated state and the covariance, and go to the next time step, and that will become the background for that time, and I will do update, right? So there is this push forward in time. You run your model from this time to that time. That gives you a background, which is xb now. Well, let me put this once here, 2, and then b2, and this will give you a xu2 and bu2. By using effectively the same kind of formula, I just put 1s and 2s all there, right? And then keep doing this. And the main problem doing all this for any kind of reasonably large problem is that you can't update this. This is n cross n. So even for a small model, say Lawrence 96, 40 by 40 dimensional model, this is 40 cross 40. And solving, well, I mean, that's maybe possible, but once you go to large models like weather models, you don't want to do this. And that's where the Ensemble Kalman filter comes in. What you represent this by now, instead of thinking of this as simply a point with a covariance. So what are the covariance? One way to sort of visualize a covariance is an ellipse, right? So suppose B has eigenvalues and eigenvectors, which it does because it's positive definite matrix, so it has positive non-negative eigenvalues and corresponding eigenvectors. So I can represent that by calling this as x1b, and then there is a ellipse in that n-dimensional space whose major and minor, whose axes are aligned with the eigenvectors, and the length of the axis is proportional to the eigenvalues, right? So what this represents in picture, then you have this ellipse, the background ellipse. You have an observation which is in a different space, so I can't draw it on the same diagram because y is an n-dimensional object. So it's in some space, but it has a associated error covariance matrix. So this is y. There is a mapping which takes me from here to here, which is h, which I can't invert. So if most of the times we'll be basically looking at the case m less than n, and so I can't invert this matrix. But after combining the two, what I get is a xu with a new updated ellipse. Well, this should be at the center of this ellipse, but at 1. And the Ensemble Kalman filter fills up this ellipse with dots, effectively. Right? So you represent the error covariance by a whole bunch of states, usually 80, 100, something like that. But remember the pictures that Eric was showing of these dots in that plane, or they could be along a line. So that was what he was talking about. The singular values are square roots of these lambda 1, lambda 2s. Right? So you fill up this with dots, and there is a corresponding formula for updating each of these dots. So if I call these the background dots, the Ensemble Kalman filter gives a formula for going from the black dots to the red dots. So each of these points will shift by some amount, such that the mean of these red dots is given by this formula, and the covariance of these red dots is given by this formula. So you are given black dots whose mean and covariance, whose mean is this and whose covariance is that. You want to find the red dots whose mean is that and whose covariance is the updated one, right? And that's what the ensemble Kalman filter does. And the formula is actually very simple. I wish I could actually get this to use, but anyway, I guess I can erase. Oh, I could. This much is enough, I guess. Yeah, I was thinking of. No, that's okay. I wanted my laptop on at some point, so anywhere is fine. So. State, it's a state vector. So let me call each of these dots by a name. So now I'm going to drop this 1 for the time index, right? The time index is there somewhere implicit. So each of these dots will be the ith dot, the ith background dot is xib. So I have I going from 1, 2, 3, let's say up to 40 or 100 or whatever you want. So each of these is basically a state vector. The formula I want is the updated, the red dot, which is xiu, and it is simply just that. It turns out that that works. K times y. There is a bit of a hitch, which is what this is about, minus h of x b I. So it looks exactly like this. Effectively, you are applying Kalman filter, if you want to call it, to each and every ensemble member, each of the dots. Yeah. With one little hitch, which is this, that you have to sort of say you can't use exactly this observation. For each different dot, you need a corresponding dot in the observational ellipse. So you can't use the center of this ellipse to, yes?
So when Eric was talking about the variance solution, you're taking the dot from the top of it?
No, this is on top of it. No, this, yeah. The variance inflation goes on top of this. Yeah. Yeah. Yeah.
For x, we need a corresponding one on the point.
Yep.
Suppose if we are having a lot, y is the observation.
Yeah.
We are having a lot of observations.
Yeah.
So can that be multiplied?
So the whole lot of observations, suppose you have 10,000 observations, then my y is a 10,000 dimensional vector. So your set of observations is one point in this 10,000 dimensional space. So that's one dot here. This is a 10,000 dimensional space. Right? This dot is in a 10,000 dimensions. Right? So to each of these components, you need to add a perturbation. What kind of perturbation I will describe in a minute, but to each of these 10,000 components, you add a small perturbation. So you move around in that 10,000 dimensional space. So no, that's different. These are not the different observations. The whole set is described by one point. Yeah. So in this case, m will be 10,000 if you have 10,000 observations. So okay, and this is different from the covariance inflation, if you know what that is, that Eric was talking about. That's on top. Yeah.
What is the letter for that?
Delta. I mean, yeah. And so what is? Yeah. So that's why I was just coming to. So two things that we don't know about: what is delta and what's k. Because k needed b, but we don't have b. We only have dots. We only have dots that occupy ellipse. So how do you calculate the b from these dots? So that is simply the formula for the ensemble mean and ensemble covariance. So b is then approximated by, let me call it b ensemble, which is simply 1 over the factor which I always forget, so I will write it at the end, I going from 1 to, so let me call this number as capital N, xib minus x bar b, and xib minus x bar b, transpose, sorry. Right? So have you, so well, that's basically the definition of a ensemble covariance for a given ensemble. So, and what is x bar b? X bar b is simply the ensemble mean. Yeah. So I take the mean of the ensemble, I subtract the mean off from each of the members, take that, its transpose times this, and then I'm done. Okay, so a more
Connection to the talk earlier.
sorry.
Can I make a connection? to
Sure,
the earlier
yeah.
talk? So the sample mean, he has n samples from this distribution. Right, so the sample mean he has here, which is the mean of the ensemble.
Yeah.
So if you had an ensemble members, they have a mean, but that's also sample mean from the bigger distribution that those are coming from. Those two are the same thing here.
Yeah, exactly. So this is okay. Yeah, good. Thanks. So I guess this is supposed to approximate the mean of the Gaussian distribution from which this is supposed to be drawn. That is, this is supposed to be approximating E of simply x with respect to f, where f is exponential, well, here, minus j0 of x. Sorry, jb of x. And this term is jb. F is, sorry, yes, f is proportional to that thing. Yeah, so this is the Gaussian with a mean xb, covariance b, and this is then the mean of that Gaussian, which is xb, which is supposed to be xb. So this is supposed to be approximately equal to xb. The mean of this we know, which is xb. Okay. So there is a more succinct way of writing this. This is kind of complicated way of writing it. So let me write a matrix which is ZB, yeah, which is x1 minus x bar b. That's a vector of length n, right? The first ensemble member and its deviation from, the deviation of the first ensemble member from the mean of the ensemble, x2 minus xb, that's another vector of length n, all the way up to x capital N minus xb, okay, bar, right? And that's, so what's the dimension of this matrix? It's n cross n, but yeah. So it's small n cross capital N, yeah? Okay, and the way to write this formula is, if you notice, I'm taking this and the transpose of itself. So if I take the transpose of this matrix, you will flip these over, each of them, and what you will get is exactly that. So basically, the B ensemble is equal to 1 over n minus 1 ZB times ZB transpose. Yeah? That's just a simple calculation, that matrix multiplication. You can do it and you can see that that's true. Yeah? Okay, and so what's the a slightly more, so that's about k, and this was just to write that. And what's delta I? The delta i's are supposed to represent this ellipse, right? So what should they be? Okay, let me make a so these black dots here are supposed to represent this Gaussian distribution, the ellipse of mean xb and covariance b. What do these black dots represent? The observation y with covariance which is gone now, r, there, yeah, it's gone, right? So what should they be drawn? What should the mean of these black dots be? The mean of these dots here should be, no, we don't know hx. X is what we want to find, so x is not given. So it should be just the observation that we started with. So that means that if I take them, so each of these black dots corresponds to y plus delta I, which means if I take the average, the ensemble average of these, that is, if I take some I going from 1 to capital N of y plus delta I want it to be equal to y, or well 1 over n of this, which means that the delta I should be mean 0. So delta i's must have mean equal to 0. And how about the covariance? What should be the covariance of these delta i's? Sorry? Oh, yeah, the formula. So the formula for the covariance is simply I going from 1 to n, 1 over n minus 1, delta I transpose. That's a covariance. What do I want this to be? Please say it, it's okay. If you, I mean, there are only so many matrices. So you can, if you give me 6 answers, you will get the right answer for sure. Right? R, right? So it's the observational error covariance. So this should be approximately equal to R. What that means is that these delta I should be a sample from what? From a Gaussian with mean 0 and covariance R, right? Okay. So the way to write this formula is the following. Just like I constructed a matrix ZB, I can construct one which will be, say, ZU. So let me write this as, and so this step I don't want to go through the derivation right now. It will take too long. So basically there is a way in which you can, so to say, massage that formula in such a way that you write it in terms of matrix multiplication simply. Right? So you want to find a matrix M such that you can write ZU as ZB times M. The only condition that you need on it is, or what's the condition that this ZU should satisfy? So this is, I mean, this ZU is supposed to represent exactly these kind of things, except for now not for the background, but for the updated ensemble, right? So I guess I should have these all everywhere here. Sorry. So what equation should this ZU? I mean, what's the requirement on this ZU? What's the updated ensemble covariance if I give you a ZU? Sorry? But remember the ZU already includes the mean taken off. So I give you a ZU with the mean taken off. So yeah, but the definition of ZU is simply exactly this: replace all the B's by U's. So the mean is gone from each of the columns. So yeah, okay, suppose I do the subtraction and then what should ZU transpose be? Or over divided by n minus 1. I'm sorry? Which is this, right? Which is BU, which should be equal to I minus KH times B. Or what was B? B was approximately B ensemble. So this is approximately equal to I minus kh times zb transpose over n minus 1, right? So that's the only requirement. Effectively, I need to find a matrix M such that this equation is satisfied. There is infinitely many choices of this matrix. In fact, this is not the only way. You may want to also think about writing it as ZU is equal to M times ZB. So going back to what Eric was saying today morning, basically what you do is you look at linear combinations of the columns of ZB, the space spanned by ZB, and look at the appropriate linear combination which will give you a covariance which satisfies the requirement that the covariance is equal to I minus kh times the original covariance. That's the only requirement. And then there are infinitely many choices of this. So the algorithm which I will give you has one specific choice of this M, but that's not the only one. There are many different choices. In each different choice of M, writing it either this way or that way corresponds to the different flavor of ensemble Kalman filter. And there is at least 5 or 6 of them easily, maybe not, if not more. Yeah. So they go by the names of ensemble transform Kalman filter, ensemble adjustment Kalman filter. There is something called the reduced order Kalman filter, which is in a way similar, slightly different, but well, reduced order or something like, I keep forgetting the whole name of it. But anyway, there is a whole bunch of these kind of filters, right? In particular, this one actually uses the reduced rank approximation of the matrix Z that we talked about 2 tutorials ago or whatever. So you use this matrix, find its SVD, reduce the rank, and work in the smaller rank space and so on. So okay, so now coming to this is not quite visible. So let me write down the names here. So so I have a few subroutines. One is, what is it? So SAMP sorry. Then you can see that here, ET. These files are already on the web page, which is usually what you were using, right? And the third file is okay. So what's the idea? So this is actually just one. So what I have given you in these 3 files is simply a single step of this. Okay. The one step ETKF basically does this, and it does. So there is one more formula I forgot to mention, which is useful. Okay, sorry. So the Z, if you do something like this gives you the updated deviations from the mean, but this does not give you the mean. The mean is obtained. The formula is the same. You just put the mean on top of it, and that's it. The y remains y now, not y plus delta I. Yeah. So the ensemble Kalman filter can be written effectively like following. You update the mean according to this formula. You update the deviations from the mean according to a formula like this, so that this condition is satisfied. And that's it, then you have the new ensemble, and then you take that new ensemble and push it forward to the next time. So this subroutine simply does that and that. So what are the inputs needed to do all this? You need the background mean, you need y, h, or rather hxb, and you need zb. And it turns out that this matrix, of course, I mean, it has to depend on the, so it has to have h somewhere, right? So the specific form which I am using requires, this one requires h times zb as well. So the subroutine takes the inputs zb, h times zb, x the mean background, h times x background, x mean background, the observations, the sizes of each of these vectors, and out comes this and that. And I think what I will do is maybe you can use it, and then I will tell you what each of the steps, what it is supposed to be doing. So how do you check this? How do you test it? I mean, how do you actually visualize? How do you understand what is being done to the whole ensemble? Right? So one way to do it is to take a Gaussian ensemble, a Gaussian background ensemble, which will correspond to dots like these, that you can simply plot, right? Suppose it's a two-dimensional problem, so that this is n is equal to 2 and this is x1, x2. So if you choose a prior, if you choose a background covariance B, a 2 by 2 matrix, positive definite, and a background mean, and sample that Gaussian distribution, you can plot it, you can see the ellipse. A observation is just some number that you may choose, and use the Ensemble Kalman filter to update and see how that ellipse changes. How do you check whether what you got is correct or not? Sorry? Okay, that's part of the tutorial. Somebody should explain at the end of it how you check what you got out of this subroutine is correct or not. Yeah, and that's just one step. So by the way, there is, along with it goes a test one-step ETKF, which has each of the steps, so to say, laid out. So let me now show those. So this, oh, by the way, so for this you will need a way to sample Gaussian distribution functions, and that's what this does. This one is simply a small subroutine to sample Gaussian, multi-dimensional Gaussian distribution. You specify the dimension, no, in fact, you just specify the mean and a covariance matrix, and it will give you a sample from that Gaussian distribution, ensemble of samples from that Gaussian distribution function of the size specified by you. Yeah, so it takes a mean, a covariance, the number of samples you want. Well, so because sampling involves, so I specify a seed so that repeatable experiments can be done. So you can set the seed to be, so do you know what, okay, anyway, so if you specify the same seed, you will get the same random numbers again. That's the only thing, so that's why the seed. If it's not positive, then it just chooses a random seed. Right? And a flag is, okay, so there is a little bit of trick. For now, just use 2 for the flag value. I will explain for what the flag does later. Right? Okay, so that's the SAM Gauss. So from this you can specify any dimensional mean and any dimensional, the same dimensional covariance matrix, and you will get a Gauss, a matrix of samples from that distribution function. Yeah. Yeah, it's put into a matrix. So if you want, if M is little n dimensional and this is capital N, this matrix will have a size which is little n by capital N, just at ZB. Yeah? Okay, so that's one function. The second function, okay, I should open it here itself. Open one step. So let me just open the test it one step. Okay, so what do I need to choose? The dimension of the state, a mean, the size of the ensemble. Okay, so this is a little trick. How do you get a general two-dimensional ensemble? How do you get a general two-dimensional covariance matrix? You first choose the eigenvalues of the matrix, and you choose the angle by which you want to rotate that covariance matrix, the ellipse. And so basically if you choose this and if you choose this, the eigenvalues and the angle, then you get a general two-dimensional covariance matrix. So that's what this part does. And then this one simply samples question. Sorry? Oh, so this should be V1. Okay. So if you have already downloaded it, please. So this was the old version of it. The new one is _V1. That's what it should be. The one on the website is the one without V1, but yeah. Okay. So that generates the ensemble. Then I simply take ZF to be the square root of to represent this, I can redefine ZU to be that divided by the square root of it. So when I simply can write ZU transpose as the ensemble covariance, right? So that's why the square root of n-1, but that's just in. And then, so that's my ZF. And then I choose some observations. This is some random example, so to say, right? And then I do the one-step ETKF. And then you have to plot this ensemble, right? So that way I will leave that up to you. I haven't put in the plotting subroutines here. So, okay, what will you put to plot? The plot will be plot, for example, you have the old, so this one has a size which is capital N by, so capital N, little n cross capital N. I want to plot, say, if it's two-dimensional, I want to plot the first versus the second. So I will plot this as ZF1, colon versus ZF1, 2, colon, right? And that will plot the prior ensemble. I guess F here is B, that is the forecast or background, right? And then you can plot similarly, you can do something like hold all and plot the. Oh yes, sorry. If you don't plot with dots, you will get a whole bunch of lines, and yes, that connects all the dots, which doesn't look good. Yes, thanks. Yeah. Oops. And then you can plot the updated one, which I call it ZA, the updated U instead of U. Okay. Right? And so then you can see how the thing is shifted and so on and so forth. Yeah. So okay, that's effectively that. And so what's part of the one part of the tutorial is basically to play around with this and see if you can understand what this is doing to each of the Gaussian ensemble members and so on. And then by then I will also put, which I haven't yet copied, on the website, say Lorentz 63, but I think most of you will have And I don't know if I need to copy, but I will copy one copy anyway. It'll say Lorentz 63 model. So what is missing from this right now is the push forward, right? So you want to go, you have done the update, one step ETKF, now you take your updater ensemble, go forward with the model, that's just a for loop, and then do the update again and keep doing it and so on and so forth, right? Which is what I have. I will copy the Lorentz 63 model into the same directory. So let me just write the name. So it will be so this will simply take you. So I guess for that you will need to choose the state dimension to be equal to 3 and so on and so forth. So yeah.
It doesn't have a T.
Oh, sorry.
It doesn't have a T in its name.
Oh, sorry. That Lorentz does not have a T in its name. Okay. So I think that's we can then now we can start playing around with this. And of course, it will be great if you do look at what's inside this and what it does, and ask me questions about what it does, right? So I will wait for your questions. I have not explained what this does, right? But okay, so I need to find my Lorentz subroutine.